This is the introduction to section 2.8. It might say 2.6 on the top of this, but we'll fix that. Here we are going to put implicit differentiation into use in some context. This context is the context of related rates, where things are generally changing with respect to time. So the first example here I'm going to do out of context, and then the second example will be in context. And then there's not a lot else to say except for you to try to tackle these on your own on the activity. And of course, I'll post that video as well. So the first example says, suppose x and y are both differentiable functions of t and are related by y equals x squared plus 3. Given that dx dt is 2 when x equals 1, find dy dt when x is equal to 1. Okay, so here's what we've been given. I think when we see these problems, let's write down a sense of everything we know. We know that y is related to x in this way. We know that we're thinking about this situation when x is equal to 1. We've been told that when x is equal to 1, dx dt is 2. And we've been asked to find dy dt. Okay, I took all of that from right here and then right here. Dx dt equals 2 when x is equal to 1. Find dy dt. Okay, so now, previously we took derivatives with respect to x. Now x and y are both functions of t. And so instead here we are going to implicitly take derivatives with respect to t. So we're going to implicitly take derivatives with respect to t. Okay, so the derivative of y on the left-hand side of the equal sign, the derivative of y with respect to t is dy dt. We're going to use that notation here instead of the y prime notation because we are taking derivatives with respect to time or t, and we want to remember that. On the right-hand side of the equal sign, the 2 goes down. We go to 1 less power. But then we need to multiply by the derivative with respect to t of the inside function, and in that case is x. So multiply by the derivative with respect to t of x. And the derivative of 3 with respect to any variable is 0. So there's the derivatives with respect to t. And just as a note, what really happened here is the 2 came down, we went to 1 less power, and we multiplied by the derivative of x with respect to time. That's the inside function. So really the chain rule. Okay, so we were asked to find dy dt at a whole bunch of specific situations. X is 1, dx dt is 2. So dy dt is equal to 2 times, this is all happening when x is equal to 1 times, and when dx dt is equal to 2. So that would tell me that dy dt is equal to 4. Okay, that was completely out of context. And so let's do this similar idea in context. But what are we doing is we're going to have multiple variables, generally 2, that are both functions of time or the variable t. And we're going to relate them in some way. This way we were given the relation. And we're going to take derivatives with respect to t implicitly and then try to analyze the information that was given. Okay. Here's their second example. Consider a cylindrical water bottle that is being filled at a filling station. Assume the water bottle has diameter 3.6 inches. Okay, so what do we know about our water bottle? All we know is that the diameter is 3.6 inches, and I guess that would tell me then that the radius is half of the diameter is 1.8 inches. At one filling station on campus, you are told the bottle is filling at 2 cubic inches per second. Okay, that's clearly an important piece of information, filling at 2 cubic inches per second. At what rate is the height of the water in the bottle changing? Okay, so let's think about this. The bottle is a cylindrical water bottle, so it looks something like this. It looks something like this. We'll call this the height. Here is the radius, which we've already been told. And it's filling at 2 cubic inches per second. So cubic inches would be a measure of volume. So that's been a rate of the volume. So we've been given information about the volume. So what is the volume of this water bottle? The volume of the water bottle is pi r squared times the radius h. That is the area of the base, which is pi r squared, times the height is the volume of the cylinder. Okay, but here r is fixed. It's just some number, right? It's 1.8 squared. It is not changing with respect to time. So let's see, what other information do we need? This other information that is circled in pink is dV. It's the rate of change of the volume. It's the rate of change of cubic inches per second. So we've been told that dV dt is 2 cubic inches per second. Okay, so now we can take derivatives with respect to time. And what happens when we do that? On the left-hand side, we get dV dt is equal to pi times, well, the radius is fixed, so 1.8 squared times, but the height is changing as water goes into the volume. Oops, sorry, as water goes into the water bottle, times dH dt. What have we been asked to find? We've been asked to find dH dt. What rate is the height of the water bottle changing? So what did we want to find? We want to find dH dt. And we want to do that when we know dV dt is 2 cubic inches per second. Okay, so let's see, I guess, what do we have here? To do a little bit of work. So dV dt is 2, so we have 2 is equal to pi times 1.8. That's 18 over 10, which is 9 over 5, times 9 over 5 squared, times dH dt. We're running out of space. Let's see if we can fit this in here. So we have 2 times what, 81 over 25, so 81 pi over 25 times dH dt. And if you multiply and you find dH dt, we'll multiply by 25 over 81 pi, so I think we get 50 over 81 pi. And what would the units be for dH dt? Well, the height is measured in inches, so this would be inches per second. Okay, so at a second filling station, you're told the height of the water bottle is changing. At what rate is the bottle filling? Okay, so it's the same scenario. So our volume in this case is pi times, what did we decide it was? 9/5 squared times the height. So the two things that are changing with respect to time are dV dt and dH dt. And we've been told the height of the water bottle is changing at 1/2 an inch per second. At what rate is the bottle filling? So the rate at which it's filling is the rate of change of the volume with respect to time. The derivative is going to look exactly the same as above. dV dt is equal to pi times 9/5 squared, that's just some number, times dH dt. But now instead of being given dV dt, we've been given dH dt. So dV dt is pi times 81 over 25 times 1/2. Multiply that across and we get 81 pi over 50 this time. And now the rate of change of volume, well, volume is measured in cubic inches, and time here is measured in seconds. Okay, there's a couple examples. The key is relating the pieces of given information and see if you can use those in the rates of change that are given to tackle the activity for section 2.8. Might also help to read some of the examples in the textbook before you dive into the activity.